Great pleasure to introduce our keynote speaker today, Professor Mark Campbell from University of Limerick. Mark is a cognitive psychologist and he is also the director of the Esports Science Research Lab at the University of Limerick. And his work bridges psychology, neuroscience and performance science. And he's published extensively in the areas of perception, attention and neurocognitive performance enhancement. And in particular, he has an interest in applications of research, particularly in expertise and human skill and adaptability and high performance learning in digital environments, which sounds good given the area of AI and big tech, Mark. Very, very importantly, Mark did his PhD a long time ago at University College Dublin here, and in particular he was supervised by Professor Aidan Moran. And as part of our research day is to celebrate Aidan's contribution and his lasting legacy in the school. It's particularly lovely to have you as a speaker, so thank you, Mark.
That's great. Thank you very much, Nuala, for those kind words. I'm feeling a bit old now, saying all those years ago. I started in UCD in 1998. One of my first lectures was with Aidan Moran. And he coined the phrase, which he did oftentimes, sport is played with the body, but won in the mind. So that sort of opened my whole world up to what psychology was, because I came to UCD thinking I was going to be the next clinical psychologist, like a lot of psychology students. And about 6 weeks into cognitive psychology lectures with Aidan, 6 weeks into perception lectures with Nuala, and 6 weeks into Teresa Burke's neuropsychology lectures, and Kieran Benson, I suppose, really just opened my eyes up to what psychology could be, and I suppose that whole side of experimental psychology, and how your mind or how your cognitive attributes might actually drive your path to expertise or your path to performance. So the title of my talk today is this idea of the cognitive athlete, and maybe exploring skill learning and neuroplasticity within gaming and esports, but I'll explain a bit more about that in a little while. So we talk about coming full circle. Aidan was my PhD advisor. I was very fortunate to have Aidan as my advisor. And my first PhD student was Noel Brick in the middle here. And Aidan was his external examiner, which I think is really nice when you consider the kind of cycle of PhD supervision. So I just wanted to note that. Joe, I had black hair back then around this date, so I decided to do a meta-analysis. Aidan's most cited paper was a mental practice meta-analysis, so I approached Aidan and said we should replicate that and update it. And I have grey hair ever since, so I don't know about that. Okay, so we have a long history of being fascinated with mind sports. We go back to the ancient Olympiad, we go back to ancient Rome, ancient Greece. We were obsessed with war games, chess, winning things by power of our mind, our cognitive attributes, our problem solving, our decision making in kind of various circumstances. And I suppose when we fast forward to today, we kind of think about this kind of digital age we're entering or we're in, where there's a lot of AI, there's a lot of digital environments that we're kind of navigating. And we think maybe we've had a long fascination with it, but we've had a short past of kind of empirically scrutinizing some of this area. A couple of years ago, we tried to conceptualize this idea of a sports continuum. So the sports continuum goes from your physical to your cognitive. And far right, we have our kind of mind sports, chess and esports. And far left, we have these, what are thought to be primarily physical sports, maybe your rugby and athletics. So when we look at mind sports, we think about chess normally. And when we think about chess, or when I think about chess, I think about the cognitive revolution in psychology. I think about the genesis of where we really started looking at cognition, being really interested in it. And it started in the 40s with Adrian de Groot here looking at thought and choice in chess. Looking at decision making and problem solving and all these cognitive attributes associated with people learning or trying to play chess, and there was a lovely ranking system within chess, the ELO ranking system. And it was a lovely natural lab. We could record everything that everyone was doing. We could record the moves, we could work out the probabilities of, well, that was the best move or the next best move, and it was a really nice thing to do. And other researchers were very interested in this. John McCarthy over here, the godfather of AI, first coined the term artificial intelligence in 1955, published an article called Thought and Intelligence, where he was trying to teach a computer how to play chess. So again, chess is sort of driving this cognitive revolution. And then lastly, we could come on to Newell and Simon here, who went on to win a Nobel Prize for their work in memory, chunking in particular. And we see their research is the simulation of human thought in 1959. So this was really the start of a huge push in psychology into cognition, cognitive science, and that kind of frontier of what's actually possible, what's measurable, how do we quantify some of this. So what does chess have to do with esports? Well, esports is the new chess. So esports is the competitive playing of computer video game, all the way through to professional levels. As you can see here, this is a stage in a big stadium where we have two teams of 5 playing each other, and their avatars are displayed on the screen here. This is a computer game called League of Legends. And they filled out the stadium, so it's kind of a big deal, right? Here's another view from a different tournament here. Let's look at some of the numbers. So 2025 market value is over $300 billion. There are 3.32 active video game players on the planet, which is a hell of a lot. Gaming revenue is over 500 billion, and the games industry is worth double music, film, and TV combined. So for people who aren't familiar with gaming, it's a really big deal. And when we think about, I work in the sports science department, so I'm very interested in human performance and that kind of path to expertise, how people train. And we look at esports, and there's 1,300 esports teams and organizations out there, professional teams competing for millions of dollars in prize money. So it's not just the misconceptions which might be out there about gaming. The misconceptions might be out there. Might be. Anyone recognize this guy? It's Christian Bale, future Batman. It's a bit of a challenge to work him into a presentation about gaming, but he's playing as Atari here, believe me. So the misconceptions are, gamers aren't 15-year-old boys at home in their parents' in their bedrooms playing on their own. You know, with the advent of broadband, everyone is hyper connected. It's a really, really social activity. Most gamers are over 50% of gamers are adults. The average age of a gamer is 33. 44% of gamers are females. And then when we move into esports, the really trippy thing, the average age of retirement of an esports professional is what?
26 is the reaction time.
23. Okay? So there's this really outdated misconception that your reaction times slow down and that you're no longer a good gamer. So by the age of 22 or 23, these professional organizations, some of which are the biggest sports franchises in the world, are just getting rid of all these gamers because they've slowed down. So a big mission and part of the lab work we do is to sort of look at sustainability of performance and look at practices of how people perform and how they play and their approach to this. Because, you know, the bad news story is that gamers sit for really long periods of time and rage at their screens and all this kind of stuff. And the good news is that maybe these people are really good cognitive athletes and that they can actually apply these skills into a whole domain. So I'm not really a gamer. I had a Commodore 64, so I guess I could call myself an OG gamer, but I was a golfer. I was more of a golfer. We were talking about ID earlier, identification, so more of a golfer. But I saw this around 2015, Red Bull were getting into sponsoring gaming teams, and they talked about, you know, gamers, professional gamers, as being these sort of high-performance human-computer interaction experts. And this idea of integrating technology with all the other aspects around it really struck a chord with me because, you know, for the first time I realized that it probably was the new chess. You know, it's a digital environment. We can record absolutely everything they do in this digital environment. We have so much experimental control over what we can do there, particularly around intervening or experimentally kind of manipulating things, which is what I like to do in psychology, as you'll see as I go on. But so for the first time I thought this would be a really good avenue to get involved in. And down in the University of Limerick we have a software research centre who used to be an engineering software research centre, so programmers, hardcore computer scientists only, and they kind of broadened out their reach based on what industry were demanding, and industry wanted to know about, you know, what are the key performance indicators in gaming. Nobody had done it, no research on it. So we started off looking at key performance indicators in gaming, and gaming is not just, you know, your shoot 'em ups, your first person shooters. There's a whole continuum of different types of games. So you couple this with this idea of this really unique time we're living in. We're living in this really unique time. The current generation, Gen Z, I'm running out of letters, I'm not sure which, are the first generation really kind of completely immersed in digital life. You know, they're really, really skilled. They have a lot of digital intelligence. So they might have a lot of unique skills. These skills might be expertise in prolonged human-computer interaction, maybe in a seated posture, typically. They might be really skillful and efficient communicators because gaming is hyper-connected. You don't game on your own anymore. There's no such thing as gaming on your own. You game in teams of 4 or 5, typically. And there was a lot of research starting to come out, starting with Daphne Vivellier and a couple of Swiss psychologists around enhanced cognitive abilities of gamers when compared with non-gamers. So that really got me interested in maybe exploring some of this, and we had an industry partner, Logitech, who wanted to look at KPIs in gaming, so it just gave me a lovely free rein to kind of tackle some of these things. So I started to think about the types of work we could do, but I wanted to start with our little basketball ninja here. It's pretty good. How does the brain learn? So how does the brain actually learn? How does motor learning start, and where does it finish, and what's this kind of loop look like? And when we think about this, it starts at that kind of cognitive level. It starts at the memory level. It starts at that motor program, memory trace, different terms used in different disciplines. And then we produce this action. This action could be pressing your controller or your keys on your computer gaming, or it could be like our little dude here throwing basketball free throws. What we get after the back of this is sensory feedback. This sensory feedback for a basketball free throw might be very reliant on touch and feeling of your wrists extending out, or the pushing off, or the movement of your hands. And obviously what we have off the back of this is different sensory feedback about whether we were successful or not. Off the back of being successful or not, if we keep practicing or continuing to refine this, we strengthen this feedback loop, don't we? And next time we might, you know, we've missed it left, so next time we might try the release pattern from our basketball free throw and kind of throw it a bit further to the right. We get this lovely feedback, and we get this lovely wiring of what it is we're trying to learn and how we're going to learn about it. So keep this in mind for later, because later we're going to just introduce electricity along the green part of the brain there. Okay, so let's get back to quantifying performance. So anyone heard of Space Fortress? Really great game from 1981. Space Fortress was designed by psychologists to measure problem solving, decision making, lovely cognitive attributes. And there was different parts to the game, so you had to do different parts to kind of be successful in terms of your missions and things like that. I'm not going to get into it, it takes ages, but I want to show you a study which really sort of got me thinking about this idea of cognitive athletes and how we can train and how we can improve what they're doing. And it was by Walter Booth and colleagues, and it was 2010. They used Space Fortress, but what they did was they used these kind of principles of sports science. Or Anders Ericsson, a colleague of Aidan Warren's who was here, I went to see him here years ago, talked about deliberate practice of elements of a sport outside of it. So if you were a golfer, you wouldn't just practice playing golf, you might practice your driving, your putting, your chipping, your irons, etc. So that's exactly what they did in this study, except they used stupid terms like variable priority training and full immersion training. Full immersion training is just playing the bloody game. Variable priority training is just doing different parts of the game, isolated out separately. And as you can see here, 2 or 3 practice sessions in, they're already significantly better at performing in the game by practicing the isolated components of it. So being in a software research centre, I thought this is great. I'm going to get some software person to start making me software tests which can measure different parts of gaming. And we can kind of marry them up maybe with my interest in cognition. When we think about cognition, we might think about there's kind of some key domains really we might be interested in for gamers. Working memory, episodic memory, declarative memory, maybe psychomotor speed, so your simple reaction time, your complex reaction times, obviously executive functioning, and of course attention or concentration. So for people who aren't familiar with some of the cognitive tests, I'm just going to show you a few of them very briefly, and then I'll show you some really interesting results off the back of that. So we might take something as simple as the Corsi block tapping task. The Corsi block tapping task is a series of boxes which light up, and you need to remember the pattern in which the boxes lit up. Okay, you start off at 3, you end up going to at least 10. 8 would be an excellent score to remember. So what's it measuring? It's measuring this idea of location and working memory and the pattern or the order which they came in. And the variables of interest then is the block span, or what you can remember. This next one hopefully doesn't have audio, so it will really annoy you. Is our... You have to remember the maze. So anyone here with the Groton maze, you have to do it 6 times. Shut up. Okay, so the first time, I'll go back and just show you in a second. The first time you do it, you have to remember it's trial and error. You're pressing the next way over, you start up in the top left and you work your way down to bottom right. You do the same maze with the same path in it 6 times, so we can measure the rate of learning of a completely independent maze route. So it's a really nice measure of learning efficiency, information processing speed, and more visual spatial memory as well. And our variables are the errors you make and the types of errors you make, perseverative errors versus other errors. Okay, and then we move on to the Stroop test. The Stroop test is this gorgeous test. I don't know if you're not familiar with it. It's name the color, not the word. So we have a really kind of hardwired ability to want to read a word rather than name the color of the word. So we get these lovely congruent trials where blue is displayed in blue ink, and it's lovely. We go, yeah, blue, got it. And if it's blue and red ink, we want to say blue, and then we have to say red. So we have to inhibit our kind of pre-learned hardwired action to state the correct answer. So it measures simple attention, and it measures kind of more complex attention or response inhibition. And then it measures our simple attention, and it might also tap into this idea of interference control. And then a final cognitive test I want to make you familiar with today is, and the variables are accuracy and reaction time. Final test I want to familiarize yourselves with today is the trail making test. Trail making is a really nice test. It comes in 2 parts. Part 1 is just you start at 1, you draw a mouse to 2, to 3, to 4, to 5, all through the map. Sounds really simple, doesn't it? It measures visual information speed, visual processing speed, information processing speed. Trail B then introduces a rule. The rule is that we have to go from a number to a letter to a number to a letter. Okay, so again, we're stopping ourselves, we're inhibiting ourselves from just going straight to 2. We have to go to A, back to the number, back to the letter, back to the number, back to the letter. So it's a lovely measure of executive functioning. It's a lovely measure of inhibiting yourself to do a particular task. And the time to complete the maze or the trail is the interest here, and how many errors do we make while we do it. So 2018, a couple of us did a study where we got gamers and non-gamers. We were interested in action video game players because action video game players was really getting a lot of bad news in the press school shootings in the US was all because they were playing, first-person shooter games, this kind of thing. But the research evidence was that some of these action video games were driving some of these bigger cognitive differences between non-gamers and gamers. So we wanted to look at that, and we did a Stroop test with them. And our action video game players are here in black, and here's our congruent trial, so our blue with our blue ink, incongruent, which should be longer, control, and overall. And we measured their reaction time. Gamers are super fast. Okay? What happens when we go super fast? Normally we make more errors. What happens to gamers when they go super fast? They're more accurate. Okay, so we take a simple cognitive test. We get different population, a gamer versus a non-gamer. We see that they're faster and they're more accurate. So they're better at simple attention and they're better at that kind of response inhibition to incongruent trials as well. So really interesting, I find. You mightn't, I do. And then we looked at trail making. So what do we see with trail making? Again, TTC here is time to complete. And here we have the average numbers of errors that they're making. Again, gamers are faster at getting through the trail, and they're making less errors, though not statistically significant over here. So there's something really interesting going on. These were university students who just happened to game or not game. So they were the brightest and best that we could have down in the west of Ireland. And they were action video game players, so they were anyone who played MOBA type games or FPS or TPS type games, so shooter games or these League of Legends type games. Just to bring this on a tiny bit, because we talked about the continuum of sports earlier, where mind sports was over on the right and esports was just in there on its own. A few colleagues and collaborators from Turkey and Germany have recently looked at this, but I've actually isolated out first-person shooters from people who play MOBA games. So one is a first-person shooter game which has an action component to it, and MOBA games have slightly different demands in terms of how you play it. And here they're starting to see some evidence that on a flanker test and on a backward clock test, so again a kind of vigilance, a measure of vigilance and a measure of cognitive control, that first-person shooters are significantly better cognitively than even MOBA type players, even though we bundled them in together previously. So it was around COVID and I got this really crazy idea that I wanted to look at pre-registering some hypotheses I might have. So we went to the British Journal of Psychology and we said, here's our hypotheses. Gamers are cognitive athletes, they're deadly. They're going to be more resistant to cognitive fatigue. So we're going to cognitively fatigue them by doing a crazy hour-long Stroop test there where they have to pay attention. We measured their eye tracking, their pupil, we did everything. And we tested gamers versus non-gamers, and it took us, I went even more grey, Joe, doing this study. It took ages, it was pre-registered, so we had to wait for stage 1 approval and then stage 2, but I'd really recommend the process. And they weren't more resistant to cognitive fatigue. So, probably would have ended up in a file drawer somewhere, right? But again, what we're seeing here is across different cognitive tests, gamers are outperforming non-gamers in cognitive tests, except on this psychomotor vigilance task, which is just like whack-a-mole, just hitting a button as soon as you see something on a screen. Across the other ones here, we see that their rate of learning, so here's our maze 1 to maze 6 taken away, so that's our Groton maze from earlier. And then these are, our kind of flanker and our Stroop test again, where they're faster as well. Just a bit of a sneak peek for today, I suppose, because there is some nice autism type talks and neurodiversity talks. We're doing a project at the moment looking at neurodiversity in gaming, because when we look at professional games, professional teams, professional gamers, they are hugely overrepresented by people who identify as being neurodivergent. So we want to look at neurodivergent gamers versus neurotypical gamers. And just a really quick sneak peek, we've tested 89 people who identify as neurodiverse who are gamers, and on the Stroop test, have a look here, neurodiverse gamers are better at an inhibition and complex attention. So it's not quite over the line statistically yet compared to what we're doing, but we're testing away. We're only about 5 or 6 months into a 2-year project. But So even within gaming, we're seeing maybe neurodiverse gamers having a better cognitive profile for gaming in relation to what it is that they do versus neurotypical gamers. So, what are you thinking now? Does simply playing video games improve your cognition? Right? Or is it what has always been thrown out there? Maybe people who are really smart, really good cognitively, are drawn to play video games, so that when you recruit them, the scales are already tipped one way or the other, right? And a researcher called Craig Stark and Clements and a few other colleagues from UCI over in California have looked at this in terms of hippocampal memory, hippocampal volume, grey matter volume, and 2 or 3 really nice studies from themselves going back to 2015 where they look at this idea of environmental enrichment. And when they look at 2D video games versus 3D video games, 3D video games drives some hippocampal memory performance and hippocampal volume changes. So, there's a structural change happening in naive gamers' brains. So people who've never gamed before, when they play a 2D game, they don't see anything happening hippocampally. And when they play a 3D game, they do. And in this case, it was Mario Kart versus Angry Birds or something like that. And they have a nice take on it here. They say training naive video gamers in a rich 3D environment but not 2D resulted in significant improvement in hippocampus-associated cognition using several behavioral measures. These results suggest that modern-day video games may provide meaningful stimulation to the human hippocampus. So they went on to replicate this with young adults, with Minecraft, and they went on to replicate this with middle-aged adults. So it's good news for the middle-aged people here. I'd probably have to include myself in that now. And what they said was video games provide an avenue for intervention and possibly rehabilitation, improving memory and other cognitive functionings through the engagement of a diverse array of neurobiological mechanisms. So there's something not just correlative about gaming, there's something causative too. So playing 3-dimensional action-type video games seems to enhance your cognition and also maybe change your brain a little bit. Okay, let's keep going with this brain stuff. So, I'm really interested in brain stimulation, neuromodulation. We have some nice kit. So working with Logitech and all these industry partners, I was saying to Nuala earlier, you get some nice new toys sent to you every now and again, and you get to try them out. So a colleague of mine, Adam Toth, is a neuroscientist, really interested in GVS in particular, but also maybe TDCS and TACS. And we're really interested in having a look at this loop here, this memory to action loop, and maybe stimulating the cortex of the brain to see, can we see some different types of activities happening here. So what happens when we run an electric current over our brain? We have maybe this idea of synaptic plasticity. Okay, so there's all these ions flowing from one synaptic cleft to the other when we're performing an action, or maybe when we're imagining an action, but that's a different talk for a different day. And what we have here is when we run an electric current over the motor cortex, the M1, we raise the threshold of the firing rate of these underlying neurons. They don't fire independently, right? But they're more readily able. It's like a warm-up before performing a sports task or whatever. So that when you do actually perform the action, that the rate of firing will be ready to go. It might be earlier, it might be more. There might be more firing and more wiring happening at that point. That's if you do anodal stimulation. With brain stimulation, you can do cathodal stimulation, so you can down-regulate the neuronal firing or the threshold of neuronal firing as well, which is a really interesting area. So essentially what you're doing is you're priming these neurotransmitters, these neurons, to get into a state of where they might fire, and they might fire a bit more. This is a company called Halo Neuroscience, where they have a headset which they designed, which goes, you can play music and all sorts on this. And it has the electric current is passed through these grey kind of nubbins here, which you would wet. And some of the research we've done has been with commercially available devices like Halo and Flow Neuroscience, and some has been done with Soterics, who are kind of a more research grade, high definition type brain stimulation. Okay. And the new kit, which I was just telling you earlier, we've just got it. So the really nice stuff we can do with it actually is we can map the electrical field activity to the M1 site that we're interested in stimulating. And then we can high definition target maybe the fingers or the feet part of the motor cortex, as opposed to what we've done in the past, which is just blitz the entire M1 and hope for the best. Researching. Okay. So if we look at neurostimulation in traditional sport, I think it's important here to point out that it's not this unbelievable elixir where that promises much and delivers everything. There's plenty of null results, but some interesting results here from Kamali looking at a taekwondo kick. They found that in comparison to a TDCS sham group, which would be your active control group, they think they're getting stimulation, but they're not. The TDCS real group improved their reaction time for this taekwondo kick, and they also improved their response time accuracy and the number of errors they were making. So after, I think it was 3 bouts of 20 minutes of stimulation, so typically you would have stimulation prior to performing any of these actions because your neurons are in this excited state ready to fire once you perform these actions. I couldn't pass a talk without introducing golf. I might have mentioned I play golf already. They've done TDCS with golf as well. Park and colleagues here, 2024, they found that there's better club head speed and there's better distance. So these are 2 key metrics for kind of golf performance. And again, this is the stim group versus the sham group over the course, so I think it's 1 acute bout here. Sometimes it strikes me that maybe some of this stuff is placebo, you know. What's driving some of these results here? So just to keep that in mind. Okay, let's move on to gaming, and let's look at motor skill in esports. Motor skill in esports, most esports, the OG of esports is PC gaming. So you're using your keys and you're using a mouse. And with your mouse, you're going to move to a target and eliminate that target. Okay, so it's just a really fine sensory motor movement called a flick or target acquisition. Here's what it looks like in game. This person is about to eliminate 4 characters. Keep an eye. It's quite quick, it's quite good. This is what it might look like if you were to slow it down in terms of what the actual flick or the target acquisition movement is. So you might see your stimulus or your character. You have to move as quickly and accurately to that and fire. Okay. So it is a KPI in gaming, we know this, so some of the research we've done shows you the number of targets destroyed as a driver of skill in esports, and the time to destroy them, so they're quicker, higher skill people destroy more targets and they're quicker to do it. So a bit so what-y, but it's not really. So target acquisition is a key skill. And then if we move on to introducing neurostimulation into esports, so we looked at FPS gamers, we looked at them doing a really simple mouse movement. And we had a no-stim group, an extra control group who did nothing, basically. They just did their both baseline and their post-test, so we introduced an extra bit of rigor here. We had our sham group, so the device turned on. They thought they were getting it and it turned off almost as soon as it turned on. And we had our stim group. And here's the software we designed. It's beautiful, isn't it? They trained for 10 minutes a day for 5 days on this software test. So just flick, flick, destroy, 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 destroy. And they got their 20 minutes of stim over the course of 5 sessions over the M1. And here's what we found. So by time 3, by session 3, there's a differentiation between people who are receiving the stim and people who think they're getting the stim or the active and passive controls. It's only for left and right targets, which I think is really interesting. So the stim is not working for central targets where there's a much smaller movement. So it's just working when they actually have to move to a target. So I think that's really fascinating as well. So neurostimulation is accelerating the skill improvement among FPS gamers, and it's doing it by time 3. Remember, they're only doing 10 minutes of this. So after half an hour of flick training, they're significantly better as gamers and one of the key skills for gaming. This kind of counters the narrative of esports teams. They do these things called scrims, and scrims are just playing the game for 7 or 8 hours at a time. So that's how they train. So it's like the 1960s sports science practices. It's really in the so completely outdated. So it's really nice to be able to show that after 30 minutes of training, you can be significantly better at something. Okay. Here's a bit of a sneak peek again, I suppose. We're looking at this in sim racing now. So sim racing is a really big deal. McLaren would sponsor a gaming event every year called the World's Fastest Gamer. Okay, and in the World's Fastest Gamer, people will sim race like this. This is a game. The fidelity is really good, isn't it, between what's actually required and what we think is required. McLaren sponsored this competition, the World's Fastest Gamer, and the person who wins this sim racing gaming event gets a seat in a McLaren and a contract to race for real. That's how much they value how real sim racing is compared to the actual thing of racing, okay? And obviously you don't have G-forces, but you have all the visual components and you have all the technical demands with it as well. So we've started to look at this because we're no longer just interested in like a kind of a sensory motor flick type task. With the steering wheel, you've got 6 Newton meters of vibration, so you've got a huge amount of haptic feedback. It's a much grosser motor movement. And also we have brakes, and the brakes are really important when you're driving fast. You have to brake earlier, quicker, harder, etc. So, what are we starting to see? We've got 2 people left to test, so I think we can stand over these results here. Baseline, we have our sham and our stim group. They train for 5 days. Again, it's 10 minutes of training each day on their racing task with the stim. So the stim and the sham group are improving a lot. So they're getting their lap time way down. But the really interesting thing, I think, is the stim group are quicker, not a huge amount. But when we test them 4 days later, they've kind of retained that learning. They've retained their speed. They haven't practiced. They haven't raced since. So they've gone 4 days without racing, and they're still super fast. Whereas the other people, obviously, are a bit slower because they haven't done it for a few days. So I think that's really interesting. That's a really kind of an interesting take on what neurostimulation might do. Kind of outside the parameters of today, but we've done this in laparoscopic surgery as well with trainee surgeons and medical students, and we see the exact same thing after a rest for a bead transfer task, a kind of a lapro task. We see the improvement hold up 5 days later. They're still as good as they were without any practice in the meantime. So there's some really interesting stuff going on there that might even be in the sleep space where there's consolidation happening off the back of the stim that they're getting and the practice they're doing. So they're kind of, they're strengthening those memory traces even as they sleep. I'm not sure what stage they're in when they're doing consolidation.
Stage 2, spindles.
Yeah. So this is the overall lap time. So it's a really crude measure, isn't it? They're just faster. We stimulate them and they're better, they're faster. But what are the actual mechanisms that underlie it? Steering reversal rate and peak brake application. So the stim group are significantly better in these 2 areas for steering reversal rate. Reversal rate is correcting your tires when you're kind of racing. So when you're going really fast, it's a really key metric of being able to go really fast because you have to steer reversal rate back over the 0 line. And then peak brake application is really important. So the stim across the whole of the M1 motor cortex is leading significant differences in terms of peak application for these sim racers. So there's something really interesting going on at that kind of neuroplasticity level in terms of motor learning with the aid of some technology like a TDCS or whatever it might be. So what are your takeaways from all this stuff, all this talk about gamers? The cognitive athlete has always been here. We've always been fascinated with mind sports, war games, chess, right through to gaming and digital kind of environments. The next future is probably in that kind of AI-driven, personalized training space, so that you will have, you know, your avatar, because this human-computer interaction with gaming is that you almost become your avatar, you almost embody your avatar in the game. You know, you're part of the machine is maybe part of you. Gaming is an exemplar natural lab to study psychological phenomena. It really is, it's incredible. And you know, down in the Esports Science Research Lab, we have a multidisciplinary team, so we have data analytics, machine learning, neuroscience, biomechanics, all kind of interacting together because of the amount of control and the amount of data you can get from a gaming type situation. So the takeaways then are: skill is context bound, learning is multisensory, the feedback that drives it is really important to consider it. Neurostimulation is super promising, I would say that. Some people might say it's kind of promising, but it's not a shortcut, you still have to perform the actions. And psychology, I suppose, is kind of central to sustainable performance, particularly in digital environments where we talk a lot about cyber sickness and fatigue and all these other things as well. Thank you very much for your attention. We've done a study, we published it in Frontiers there last year, the year before, with DLPFC, stimulation for cognition. So we were interested in can we improve cognitive capabilities based off the back of some sort of stimulation protocol. We found a trend towards something interesting there, but it wasn't significant, but it was nice we were able to publish that. But we have acquired the Soterix MX9, so we can do kind of multi-site and alter the waveform. So the idea is that we might do M1 for the motor part of the task, and maybe you know, DLPFC or another kind of frontal lobe area for the cognitive capacities with that as well. So we've just got ethical approval to run some new research there. So that's kind of the next frontier that we're going into. But I do agree with you. But even with some of the laparoscopic surgery stuff we've published, we found the stim was really good for cyclical tasks. So a bead transfer where you're moving something with one hand, transferring into another hand and moving into a pot was really good. But for suturing or knot tying, we found that the stimulation didn't drive any performance improvements there because there's too many degrees of freedom. You can tie it in too many different ways. So to your point, actually, it seems to work for really cyclical, simple type tasks better than these really super complicated ones. And I think flicking is a nice example of that because you only have so many targets displayed on that 180 degree kind of screen in front of you. Like we know from all the London taxi driver studies that people's cognitive abilities kind of, they improved in one area and they use it or lose it in another area, but we haven't seen any, we haven't really looked for it yet, but we haven't seen any kind of obvious decrements in different parts of cognition. Obviously we've measured a few more parts of cognition than just the tests I showed today. But I think it's something we should be really mindful of going forward, because especially when we're looking at more expert or more elite performers, they tend to be doing that task as a large percentage of their day and their skills. So obviously there's a huge element of specialization there, and when we specialize at one thing, we tend to have a drop off somewhere else. So. Oh, we probably should, yeah. I mean, this idea of active aging is huge, isn't it? And doing cognitively demanding tasks is definitely the way to go through the lifespan. But we've tried to look at experience, or the amount of experience with gaming. It doesn't seem to drive any differences really, whether it's, you know, how much experience they've had or how long they've been doing it. For some of our studies, we've had, you know, inclusion criteria that they need to be gaming 7 hours a week, or they need to have 10 years experience of gaming, but then we would just categorize them as our kind of hardcore gamers or elite, depending on their ranking. And then we will always include the other groups as well who have less experience. They'll just be our kind of lower skill groups. So we're looking to include them, but I think there's, like, we've really tried to avoid testing under 18s. Because it's just such an ethical area around gaming. So we've only tested adults in the last 10 years, or 9 years, going on 10. Because it's easier to get ethical approval, it's easier to get university students, they're on your doorstep. There's 18,000 of them in UL, so it's really handy. But a really logical next step is into that developmental space. and actually looking at some of these kind of really interesting characteristics and skills and attributes and abilities that might be emerging as they're starting to get into gaming. Yeah, in a short answer, no, we haven't looked at narrative or story, but I think it's a really, really interesting area. What we've tended to look at is the more performative elements of gaming. So we've gone almost straight into esports, competitive gamers. There's a ranking system. We've got a high degree of measurement. We can do all these lovely things, but you know, what sustains people in gaming a lot of the time is that kind of narrative, and is what actually forms the game and what you identify with or embody in that game as well. But not something we've looked at yet. But the other side of the question then is the cognitive tests that I showed you today. Like, they're digital tests, but they're not particularly gamified. They don't look like it's a computer game and people want to do well on them. You know, they're blocks that light up and you click on them, you know. So I think some of the arguments before might have been that you know, gamers are really good at this because they're using their mouse all the time. And I'm like, everyone's using their mouse all the time now. Everyone's using a computer now. So those older arguments are kind of diminishing, I think.